Every star you have ever seen, every galaxy captured by our most powerful telescopes, and every atom in your own body constitutes a mere fraction of reality. When you look up at the night sky, you are staring at a cosmic illusion. The vast majority of the universe's mass is completely invisible, untouchable, and impervious to light. It does not reflect, emit, or absorb electromagnetic radiation, yet its gravitational grip dictates the motion of everything we can see. This phantom substance is known as dark matter. It accounts for roughly 85% of all the matter in the cosmos, outweighing ordinary visible matter by a staggering factor of 5 to 1. Without this unseen mass acting as a cosmic scaffolding, the universe as we know it would simply not exist. Galaxies would tear themselves apart, and the intricate web of cosmic structures would dissolve into a chaotic void. Yet, despite its overwhelming dominance, dark matter remains one of the most profound and stubborn mysteries in modern science. The realization that the universe was hiding something massive began in earnest during the 1970s. Astronomer Vera Rubin was meticulously observing the Andromeda Galaxy, tracking the orbital speeds of stars spiraling around its center. According to the established laws of Newtonian physics, stars perched on the outer edges of a galaxy should orbit much slower than those near the dense, luminous core, just as planets further from our sun travel at a more leisurely pace. But the data Rubin collected told a fiercely counterintuitive story. She mapped out what are known as galaxy rotation curves, plotting the velocity of stars against their distance from the galactic center. Instead of dropping off at the edges, the velocities remained flat. The outermost stars were whipping around the galaxy at blistering, seemingly impossible speeds. Based on the amount of visible matter present, these outer stars should have been flung out into the abyss of deep space, escaping the galaxy's gravitational pull entirely. The fact that they remained tethered to their galactic home pointed to a staggering conclusion. There had to be an immense invisible halo of mass enveloping the galaxy, providing the extra gravitational glue needed to keep these speeding stars in check. Vera Rubin's galaxy rotation curves were the first undeniable proof that our visual inventory of the universe was dreadfully incomplete. The luminous matter we could see was merely foam riding on the crest of a dark, invisible ocean. As observational technology advanced, astronomers found a completely different way to map the unseen, utilizing a phenomenon predicted by Albert Einstein. Massive objects in space possess such intense gravity that they actually warp the fabric of space-time around them. When light from a distant background galaxy travels past one of these massive objects, its path curves along the warped space-time, bending and distorting the image we see on Earth. This effect is called gravitational lensing. Think of gravitational lensing like looking at a candle through the base of a thick wine glass. The curved glass distorts the light, creating bizarre arcs, rings, and multiple mirrored images of the single flame. By aiming telescopes at massive galaxy clusters, astronomers observed extreme optical distortions of background galaxies. When they calculated the mass required to bend the light so drastically, the numbers were astonishing. The visible galaxies in the cluster did not possess nearly enough mass to cause such severe lensing. The warped light painted a map of something invisible. The lensing revealed colossal dark structures threading through the galaxy clusters, confirming that the vast majority of the gravitational pull was coming from an unseen source. This invisible framework was not just holding individual galaxies together. It was dictating the architecture of the cosmos on the grandest possible scales, bending light itself to announce its silent presence. Having established that this immense, unseen mass exists, the scientific community faced a far more daunting question. What exactly is it? It cannot be made of protons, neutrons, and electrons, the building blocks of ordinary matter, because such matter interacts with light and would have been detected by our instruments. It cannot be vast clouds of dark gas, nor can it be swarms of black holes, as these would leave specific observational signatures that are entirely absent from our sky surveys. This glaring void in our understanding led theoretical physicists to propose entirely new classes of fundamental particles that exist outside the standard model of particle physics. The leading candidate for decades has been WIMPs, which stands for Weakly Interacting Massive Particles. These theoretical subatomic particles are thought to be heavy, packing a significant gravitational punch, yet they interact with ordinary matter only through gravity and the weak nuclear force. The implications of WIMPs are profoundly unsettling. If they are the primary component of dark matter, then a relentless blizzard of these ghostly particles is passing through you right now, Trillions of WIMPs would be streaming through your body, your home, and the entire planet Earth every single second, completely unimpeded and entirely unnoticed. Because they do not interact with electromagnetism, they pass through solid matter as easily as light passes through clear glass. To catch a ghost, you must build a trap in the quietest place imaginable. If scientists placed a detector on the surface of the Earth, it would be bombarded by a constant hail of cosmic rays and background radiation, drowning out the incredibly faint signal of a potential dark matter collision. Therefore, the search for the invisible universe must take place deep underground, shielded by miles of solid rock. One of the most ambitious of these subterranean traps is the LUX-ZEPLIN experiment, located nearly a mile beneath the Black Hills of South Dakota in a repurposed gold mine. This extraordinary facility represents the bleeding edge of direct detection technology. The core of the LUX-ZEPLIN experiment is a massive titanium tank filled with 10 tons of ultra-pure liquid xenon, chilled to a biting -100 degrees Celsius. The liquid xenon acts as a vast hypersensitive tripwire. The hope is that out of the trillions of WIMPs passing through the Earth, one might occasionally score a direct hit on the nucleus of a xenon atom. If this incredibly rare collision occurs, it would produce a microscopic flash of light and knock loose a few electrons. Arrays of hypersensitive photomultiplier tubes surrounding the tank stand ready in the pitch black, waiting to capture this incredibly faint, fleeting signal. Yet, despite the sheer ingenuity and extreme sensitivity of the LUX-ZEPLIN experiment and similar detectors around the globe, the results have been maddening. Years of meticulous observation and data collection have yielded profound silence. The liquid xenon remains undisturbed by the dark universe. This agonizing lack of detection is pushing the WIMP hypothesis to its absolute limits, forcing physicists to confront the terrifying possibility that their favored theoretical model might be fundamentally wrong. As the silence from underground detectors stretches on, scientists are turning their attention to alternative suspects. One compelling candidate is the axion. Originally proposed to solve a completely different mathematical flaw in quantum chromodynamics, axions are theoretical particles that are incredibly light, perhaps a trillionth the mass of an electron. Unlike heavy WIMPs, axions would behave less like discrete particles and more like a pervasive, oscillating wave flowing through the cosmos. Detecting axions requires an entirely different technological approach. Instead of waiting for a heavy particle to smash into an atomic nucleus, physicists use incredibly powerful magnetic fields to try and force an axion to convert into a detectable photon of light. Experiments use specialized microwave cavities, cooled to near absolute zero, scanning through frequencies like a cosmic radio, listening for the faint, resonant ping of an axion transforming into a microwave photon. While some scientists wait in deep mines and freezing laboratories, others are attempting to force the universe to reveal its secrets through sheer brute energy. At the Large Hadron Collider beneath the border of France and Switzerland, physicists are not trying to catch dark matter, they are trying to manufacture it. By accelerating protons to near the speed of light and smashing them together, they recreate the extreme energy conditions of the early universe. When these protons collide, they shatter into a violent shower of exotic subatomic particles. The detectors cannot see dark matter directly, so physicists look for what is missing. They meticulously calculate the total energy and momentum of all the particles before the collision and compare it to the debris afterward. If a significant amount of energy simply vanishes from the detector, it could indicate that a dark matter particle was forged in the fiery collision and escaped unseen, carrying the missing energy away into the void. To truly grasp the necessity of this invisible mass, we must look backward to a time long before the first stars ignited. The most compelling indirect evidence for its existence is etched into the oldest light in the universe, the cosmic microwave background. This faint radiation is the afterglow of the Big Bang, a thermal snapshot of the cosmos when it was a mere 380,000 years old. By mapping the microscopic temperature fluctuations in this ancient light, cosmologists can observe the very seeds of cosmic structure. Ordinary matter alone could not have clumped together fast enough in the rapidly expanding early universe to form the galaxies we see today. The intense radiation pressure of the early universe would have blown ordinary matter apart. It required the gravitational anchor of dark matter, which is entirely immune to radiation pressure, to begin pooling together, creating the deep gravitational wells that would eventually pull in normal matter to birth the first galaxies. This realization radically transforms our understanding of our own cosmic origins. The unseen mass is not merely a passive bystander in the universe. It is the fundamental architect of reality. The Milky Way, our solar system, and the very atoms that make up our bodies only exist because dark matter carved out a gravitational sanctuary for them to form. We are the fragile, luminous offspring of a dark and ancient scaffolding. Despite the overwhelming indirect evidence, a small, vocal minority of theoretical physicists suggest a radical alternative. What if the invisible mass does not exist at all? Theories like modified Newtonian dynamics propose that our fundamental understanding of gravity is simply flawed. At incredibly low accelerations, such as those at the extreme edges of spinning galaxies, gravity might not behave according to Einstein or Newton. If the laws of physics themselves change at galactic scales, the need for an invisible mass vanishes entirely. However, modifying gravity struggles immensely to explain the intricate patterns of the cosmic microwave background or the colliding galaxy clusters observed through gravitational lensing. The scientific consensus remains firmly rooted in the existence of an unknown particle. Yet the tension is undeniable. The longer our most sensitive instruments stare into the void without a whisper of detection, the more profound the crisis in modern physics becomes. We are either on the precipice of discovering an entirely new realm of particle physics, or we are fundamentally misinterpreting the bedrock laws of nature. The search to detect this phantom substance stands as one of the most audacious intellectual endeavors in human history. From the frozen depths of subterranean xenon tanks to the fiery heart of particle colliders, we are pushing the very limits of technology and human comprehension. The invisible universe holds the key to our past and the ultimate fate of our cosmic future. Until we finally capture a piece of the dark, we remain stranded on a tiny shore of visible light, staring out into an ocean we cannot comprehend, waiting for a ghost to finally reveal its face.